Hello viewers, we're going to take you through the story for A-Level Physics Paper 2, and in this video we are going to go through a topic in electrostatics, and that will be electric field intensity between two parallel conducting plates. So this video is suitable for students in both Senior 5 and Senior 6 offering physics as part of their combination. So before we proceed, let's first look at the course outline for Physics Paper 2. So Physics Paper 2 has 4 parts. The first part is Geometrical Optics, where 2 questions are set, and these are the topics where a student must attempt 1. Next part is Physical Optics, where 2 questions are set, and a student must attempt 1. Then the next 2, there is Electrostatics and Electricity, where 3 questions are set from these topics, and Magnetism and Alternating Current, where 3 questions are set from these topics. Now in these 2 parts, it is a student to choose. You may choose to get 2 from here and 1 from here to make the 5 questions, or you choose to get 1 from here and 2 from here to get the 5 questions. So in total they need 5 questions, where 1 must come from here, another 1 from here, then here it is you to choose. You can choose to get 2 from here and 1 from here, or 1 from here and 2 from there. So in this video, previously we covered Coulomb's law, that is electrostatic force. Then we covered also electric field intensity at a point. We also covered electric potential at a point, and in this video we are going to cover these last 2 parts. We shall cover electric field intensity between 2 parallel plates, and also closest distance of approach of an alpha particle to the nucleus. So in this YouTube we are mainly interested in the worked examples of this book, but the notes and trial questions of all the topics in Physics Paper 2 are available in this book, Mastering A-Level Physics Paper 2, and if you need a copy or copies, you can contact me on these contacts. So now we shall start our topic, electric field intensity between 2 parallel conducting plates. So for you, we are going to derive a formula. Therefore we shall start with the relationship between electric field intensity and electric potential. Now both these terms are not weird to you. I believe you have covered electric field intensity E and also electric potential V. So now we are going to first get the relationship between these 2 terms. So here we shall consider 2 neighboring points A and B in the field of a point charge Q. So close together, note this word, close together, that the electric field intensity between them is constant. This condition is very vital, and is equal to E as shown below. So we shall make an illustration. So these are the 2 points so close together, meaning that there will be a small change in potential. Here it was V, here it is V plus small change in V. And also a small change in distance. Here it was X, and here it is X plus small change in X. And this is our electric field intensity. So if the potential at A is V and that at B is V plus small change in V, the potential difference between the 2 points A and B will be given by VAB, which is VA minus VB. So when I subtract, it will be V minus V plus small change in V. Then you realize that this and this can cancel, then this and this gives you a negative, and this one is here. So we shall call that equation 1. So we shall also come and say that work done to move a positive charge of 1 coulomb from A to B is also equal to PD and is given by VAB, which is potential difference equal to electric field intensity times the distance moved. So where is this formula coming from? First of all, we know that the formula we know about potential difference or potential is Q over R. Then the formula we know about intensity is Q over R squared. Okay, now if you look at these two formulae, it implies that if I want to get this one from this, I'll have to multiply it by R, where R is the separation. But in this case, we're using distance as x, so it means that if I multiply this, if this is x, and I multiply by its motion in x, I'll be able to get Q over x. So that is where the relationship comes from. To get potential, you have to multiply intensity times the distance or the separation. Now when I equate the two, I'll come up with this. And when I make this the subject, I'll come up with this. Then in the limit, as motion in x tends to 0, this one tends to dv dx. And basically this is the relationship between intensity and potential. So dv dx is what we call the potential gradient, and it is the rate at which potential rises with distance. So basically this is the relationship we wanted, and now we can go ahead to get the formula of electric field intensity between two parallel conducting plates. So we shall consider two parallel conducting plates A and B at distance d apart, so separated by a distance d, and between which there is a potential difference V. So let's first illustrate that also. So there are two parallel plates A and B separated by a distance d. But they say there is a potential difference, meaning we have to connect it to the battery, where the potential difference is V. So because of this potential, there will be a charge. This will be charged now, positive and negative. And because they are now charged, there will be an electric field moving from positive plate to negative plate. So we are following the same rules. Electric intensity moves away from the positive charge but moves towards the positive charge. Then what you should realize is that these ones are straight, but towards the end they are a little curved. So when they tell you to draw an electric field between two parallel plates which are charged, always remember to make these ones towards the end a little curved. So this is what I've been talking about, that the field between the plates is uniform apart from the edges. Now from this expression which we have derived in the previous slide, it implies that potential difference at all points between A and B away from the edges are equal, thus a uniform field. And therefore E is equal to V over D. So in this case, the SI unit for electric field intensity will be volt per meter. This is volt and this is meter, so it will be volt per meter. Previously, we saw that E is equal to Newton per coulomb because this formula was F over Q. F over Q. But now in this case, it will be volt per meter if I use this formula. There are three cases which you need to know. One is that if a charged particle is placed inside an electric field, it will be attracted towards a plate having a charge opposite to that of the particle. The electrostatic force of attraction acting on the particle is thus given by, so let's first see that. So if you look at this, for example, now this is positively charged and this is negatively charged. If I bring a negative charge here there will be like charges, so there will be repulsion, but here there will be attraction. So this charge will be moving in that direction, or the force will be in that direction. If I bring a positive charge, here between this there will be repulsion, but here attraction, so the charge will go in this direction. So what we are doing, we are following the law of electrostatics, where like charges repel and unlike charges attract. So the force will be given by F equal to E2. Remember we saw that E is equal to F over 2. So if I make F the subject, it will be E2, which is this. So that is case 1. Now we shall go to case 2. Case 2 says that if a charged particle is placed inside the field shown above in the diagram above and it remains stationary, it implies that the weight of the particle is equal to the electrostatic force acting on the particle. So for example, here in the diagram, for the particle to remain stationary, it should be negatively charged, such that it is repelled from the bottom. Therefore, here the electrostatic force will be in this direction towards the positive plate, and there will also be a weight. Weight always acts vertically downwards. So for it to remain stationary, it implies that this force is equal to this weight, which is mg. That means that F is equal to mg, and we already know that F is got from here, and m is the mass of the particle, g is the acceleration due to gravity. So that is case 2. What about case 3? Case 3 says, if a charged particle is moving inside the field and in the direction perpendicular to the field, the electrostatic force acting on the particle is also given by this. So we use Newton's second law that F is equal to ma. So m is the mass and a is the acceleration, and F is the electrostatic force, but should be the resultant. So resultant, what does the word resultant mean? Resultant means that, for example, if there is this force acting and there is this, so this F is this one, and there is this mg, and the particle moves upwards, it implies the resultant will be this minus mg. If it is moving downwards, then the resultant will be mg minus F. So that is Newton's second law. So you should know that this F is the resultant force. So what we should note is that the equations of motion can also be used to obtain the velocity of the moving charged particle. So equations of motion are those ones. The first one is V equal to U plus AT. Second one is S equal to UT plus a half AT squared. And third is V squared is equal to U squared plus 2AS. So with that, we can now start working out the questions. So question 1 came from UNEB 2016, paper 2, question 9b, Roman 3, and says, two metal plates A and B, 30 centimeters apart, are connected to a 5 kilovolt, note that word kilovolt, as shown below. When a small charged sphere S of mass 9 exponent -3 kilograms is placed between the plates, it remains stationary. Note this word, remains stationary. Indicate the forces acting on the sphere and determine the magnitude of the charge on the sphere. So here it means we have to draw a diagram of the sphere and show the forces acting on it. So like we said, for the sphere to remain stationary, it should be negatively charged. So this will be the weight acting downwards, and there will also be electrostatic force acting upwards. So those are the two forces acting on the sphere. But they also wanted the charge, so since the sphere is stationary, it implies that this force is equal to this weight. Therefore, I'll come and substitute for force. We already saw in case 1 that F is equal to E2 and weight is equal to mg in case 2. When I equate the two, I'll also remember that electric field intensity is equal to V over D. We have already seen that. Therefore, I can make Q the subject by taking all these ones this side to come up with this. Now, next is to substitute. Substitute for M, which is the mass, G, which is acceleration due to gravity, and D, which is the separation of the plates. Then V, which is the potential difference. It was in kilovolts, that's why it is multiplied by 10 to the power 3. Then I'll get the answer, and that will be the charge they want. It will be the magnitude of the charge they want. So that was question 1. Now we shall go to question 2, which came from UNEB 2014, paper 2, question 8D. It says, a charged polystyrene sphere of mass 2 grams, note this word grams, so it means it has to be converted to kilograms, is suspended by a fine nylon thread between 2 plates 5 centimeters apart as shown below. So it's the diagram. When a PD of 2 kilovolts is applied across the plates, the thread attached to the sphere deflects through 30 degrees. Calculate the charge on the sphere. So that means that it was attracted in this direction for it to go towards the side. So to calculate the charge on the sphere, we shall have to first redraw and then show the forces acting on that sphere. So we shall redraw the sphere and show the forces acting on it. Okay, of course the first force will be the weight. It has to act vertically downwards. I think we realize we're writing 0.002 G. Now this G is no longer grams. This G is acceleration due to gravity. We are writing mg, where m is the mass in kilograms. So the 2 grams must be converted to kilograms. Then another force will be the attraction towards this plate of 0 volt. This is the electrostatic force. Then another one will be the tension in the string. So those are the 3 forces acting. Therefore, we shall come and say that resolving vertically, this vertical component of this is upwards, and this one is downwards. So it will be this equal to this. The vertical component is t cos 30. Why? It is because the angle is lying on the vertical. So when I substitute, I'll be able to get the value of t as that. Then I'll come and resolve horizontally. Horizontally, it will be t sine 30 equal to f. Then I substitute for t to get the value of f as this. But I know that F is equal to EQ, therefore, and E is equal to V over D. Therefore, I can come and choose the subject to come up with this, then substitute for F, for separation, and for potential difference. Then using a calculator, I can get this answer, and that will be the answer they wanted. Then question 3 came from UNEB 2020 paper 2 question 9D and says figure 4 shows two parallel metal plates placed 10 meters apart in a vacuum with a potential difference of 100 volt between them. A point charge of positive 2 microcoulomb is transferred from A to C following the path shown. So this is the path they are meaning from A to B and from B to C. So the question is, if AB is parallel to the metal plate, if this one is parallel to this, and BC is 10 meters long, BC is 10 meters long, which is here, find the work done in moving the point charge from Roman 1 from A to B and explain your answer, and Roman 2 from B to C. So I think to remember under electric potential, we cover that part of work done, and work done will be potential difference times the charge being moved. And the charge being moved is this one. So the first thing to do is to get the potential difference. So let's start with Roman 1. So electric potential at A will be given by this. Now where is this coming from? Where is it coming from? We know that from here up to here the potential difference is 100. But this is midway. If you look at this, this is half of this. Therefore the potential difference must be half. And to get that half, we have to say this distance over this times this potential difference. That's how we get the 50. So in other words, it is shared, like we said, in between the plates the electric field is uniform, meaning it is equally distributed. Therefore from here to here, the fraction is 5 over the total, which is 10. Of what? Of this total potential difference. Therefore we shall come here and say that is why you see here we are saying potential at A is 5 over 10 times 100, which is 50. And the same applies to B because they said it is parallel, meaning that the distance from here to here is the same distance from here up to here, which is 5. So both are at a potential of 50 volts. Therefore work done will be charge times potential difference, which will be 0 joules. So in other words, there is no work done. Why is it so? So we shall give a reason that there is no change in electric potential from A to B. So it is 0 because the potential difference is 0. And that's what they wanted. Then Roman 2, they wanted work done in moving from B to C. So we already got the potential at B, meaning we have to get the potential at C in order to get the work done. So to get the potential at C, we have to get this distance. We have to get the distance from this plate, up to point C. Now how do we get it? If I draw this dotted line, I'll be able to get from here up to here. And from here to here, this is 60 and this is 10, meaning from here to here it will be 10 cos 60. We are resolving. Now 10 cos 60 plus this 5 will give you the distance from here up to here. So let's first do that. So we shall come here and say that electric potential at C is equal to the fraction, so the distance was 5 plus 10 cos 60 over the total distance, which is 10 multiplied by 100. You'll be able to get 100 volt. Therefore, I can now get the work done from charge times potential difference, and to be this, and that's what they wanted. Then question 4 came from UNEB 1994, paper 2, question 8e, and it says a particle of charge positive 4 exponent negative 9 coulomb is situated between two parallel plates, across which at DC potential difference is applied. When the particle is moved 6 centimeters against the electric field, this work done, 8 exponent negative 5 joules of energy is used, and kinetic energy of the particle changes by this. Calculate Roman 1 the work done by the electric field, and Roman 2 the magnitude of the electric field. So we shall start by Roman 1. So for Roman 1, we already know that we shall say that change in kinetic energy is equal to work done in moving the charge minus work done by the electric field. Remember, we said the particle is moved against the electric field, meaning that the electric field is opposing the motion of the particle. That is why you have to first subtract it off, because it opposed the motion. Therefore, when I substitute, change in kinetic energy is that, work done is that, and work done by the field is what we want. So make it the subject, it will be this, and that's what they wanted. Then for Roman 2, they wanted magnitude of the electric field. So we know that work done is equal to charge times potential difference. Therefore, work done is that, charge is that, potential difference we don't know. So we can make it the subject to get this as the potential difference. Therefore, electric field intensity is equal to V over D. V is here, and D was given the question. You'll be able to get your electric field intensity, and that's what they wanted. Then question 5 came from UNEB 1999, paper 2, question 10C, and says two large oppositely charged plates are fixed 1 centimeter apart as shown in the figure below. The PD between the plates is 50 volt. This is what is here. An electron enters the region between the plates at an angle of 45 degrees, as you can see here. As shown, find the maximum speed of the electron must have in order for them to strike the upper plate, in order to hit this upper plate. So that the mass of the electron is 9.11 exponent negative 31 kilograms. So here we have to also redraw the diagram. So we shall first redraw the diagram so that we can show the motion, the full motion of the electron. Okay, so I think we can say that it has struck the upper plate, and that's the condition they wanted. So we shall start by saying that from Newton's second law, F is equal to ma. and force is equal to electric field intensity times the charge. So we are not writing Q because it is already known that the charge of an electron is denoted by E. Therefore, electric field intensity expanded to give you V over D. Then make A the subject. So this will be the acceleration. I'll come and substitute in order to get the acceleration. Substitute for this, it is a constant. It's there, it will be available in the paper you'll be doing. Then this is the potential difference. And this is the separation to meters. To convert it to meters, this is the mass which was given in the question. So in the end, you'll come up with this as the acceleration of the electrons. Now, using the third equation of motion, remember we said equations of motion can also be used. So when I use the third equation of motion, I'll consider vertical motion. Vertical motion. That is why we are saying y to mean, this means vertical component of velocity, vertical component of initial velocity. So I'll come and substitute. The vertical component at this point is 0 because this is the maximum point. I think you remember that under projectile motion of physics paper 1 in mechanics. So this vertical component is 0 at maximum point. Then this one is the initial vertical component we have to resolve. So velocity here is u. When I resolve, it will be u sine 45. It is squared, so don't forget the square. Then 2 times acceleration. Now we no longer use acceleration due to gravity, we use the one we have got. Then times the displacement. Now why are we writing 0.5? It is because from here to here, vertically it is 1 centimeter, meaning from here to here it will be 0.5 centimeters. But we have to convert to meters. That is why you are writing 0.5 exponent negative 2 to give you the displacement in meters vertically. Now here the good thing, we have only one unknown, so we have to simplify and get that unknown, which will be this. And if you look at the question, that is the velocity, the speed they wanted. They only wanted speed. That is why we are not getting, okay, the direction was given. So they wanted speed means only magnitude. So we can't state the direction here because speed means magnitude. So that has been electric field intensity between two parallel conducting plates. But remember we said we are going to cover two parts, so we shall also cover the closest distance of approach of an alpha particle to the nucleus. So an alpha particle directed onto the nucleus is deflected through a large angle, and the smallest distance alpha particles can reach, note this word, smallest distance, can reach the nucleus is referred to as the closest distance of approach of the alpha particles to the nucleus. So you need to illustrate this. So we shall suppose an alpha particle of mass m moving with an initial velocity v collides head-on with an atom of atomic number z. The particle is deflected as shown below. So we shall try to illustrate that. So this will be the atom and this is the nucleus. So an alpha particle will come and collide with this atom but cannot reach this nucleus, so it will be repelled along the way to go back in the path it came from. Now this distance between the nucleus and this part where the particle turned, alpha particle turned, is what we call the closest distance of approach, and that's what we have denoted as R naught. So basically this is what we are looking for in this part. So we have to derive how to get that closest distance. So what happened is that the alpha particle will be slowed down until it comes to rest at a distance r0 from the nucleus and then repelled back. I think we have seen that. So r0 is the closest distance of approach, and that's what we want. Therefore, at r0, the kinetic energy of the alpha particle is converted to potential energy of the nucleus alpha particle system. This implies that if E is the magnitude of the electronic charge, the charge of the alpha particle will then be 2 times E. Then the charge of the nucleus will be Z times E. So this Z is the atomic number, we saw that, times the E. Now someone may ask, where is this 2 coming from? It is because the alpha particle in your physics 1, it was 4, 2, meaning that it has an atomic number of 2. This one, the nucleus, in the question we said the atomic number is Z, so it will be atomic number times the electronic charge. Atomic number times the electronic charge. So that is where the 2 is coming from. So here we say that they are equal, so it is converted, meaning that at this point, initial kinetic energy of the alpha particle in joules is equal to potential energy of the nucleus alpha particle system at the distance of closest approach. Therefore, if we substitute, kinetic energy is given by a half mv squared that we already know. Then potential energy will be, remember potential energy means there are 2 charges, that's why you see a Q1, Q2 over 4 pi epsilon naught r0. We saw this formula under electric potential. So these 2 will be equal, and when I make this the subject, if I'm given the rest, I can make this the subject, and that will be the closest distance of approach. So basically this is the formula we're going to be using in this part. So question 1 came from UNEB 2020 paper 2 question 9e, and it says an alpha particle of charge this and mass this travels with a velocity v directly towards the nitrogen nucleus, which has a charge of this. The alpha particle reverses direction at a distance this. So this will be the distance of closest approach from the nitrogen nucleus. Roman 1. Explain why the alpha particle reverses direction. And Roman 2. Find the initial velocity v of the alpha particle. So let's start with Roman 1. So Roman 1, we shall say that the alpha particle loses kinetic energy as it approaches the nitrogen nucleons. I think we already saw that. And this is transferred to electrostatic potential energy. Therefore, at some point, note this word, the kinetic energy of the alpha particle is lost and it is repelled back by the nitrogen nucleons. So that is one way of explaining, but alternatively you can also say that the repulsion between the charges retards the motion of the alpha particle, and as a result, at some point the velocity of the particle is below 0, meaning it is now negative. Thus, the repulsion causes the particle to reverse its direction. So any of the two is okay. Now we shall go to Roman 2. So we shall remember that on closest approach, all the kinetic energy of the alpha particle is converted into electrostatic energy of the alpha particle nitrogen nucleus system. Therefore, we shall quote the formula which you already know, and then now we are not using 4 pi epsilon naught, because we said we already know by now that K means 1 over 4 pi epsilon naught. So we shall come and substitute. Substitute, a half is there, mass is there, V is what they want, K is this, Q1 is that, Q2 is that, and separation is that. That means that my aim is to make V the subject, and V will be equal to this, and that's what they wanted. Then question 2 came from UNEB 1999 paper 2 question 9c, and says alpha particles with charge this, each having kinetic energy this, are incident head-on gold leaf nuclei of this in a gold foil. Calculate the distance of closest approach of an alpha particle to the gold nucleus, and they give you that E is equal to that. So E is a constant and will always be given. So on closest approach, we already know that all the kinetic energy of the alpha particle is converted into electrostatic energy of the alpha particle gold nucleus system. That means that these two are equal. Therefore, we shall quote the formula. Now this one was already given. Then the potential energy is K1 Q2 over R, which is the separation or closest distance. Therefore, come and substitute. I know this is that and this is that according to the question, and this is the closest distance of approach. Therefore, when I make R not the subject, this K is already known, 9 exponent 9. Then this 2e times this gives you 2 times 79, which is 158. Then E times E, which is E squared. Then this one comes down. But I already know the value of E, so I can substitute for E, and I'll be able to get my R naught as this. And that's what they wanted. So that brings us to the end of this video. Thank you for watching, and be reminded the next video will be on capacitance of a parallel plate capacitor. So if you have not yet subscribed, please click on the subscribe button below this video so that you can receive updates when the next video has been uploaded. And also, if you know of any student who is not yet on this platform, please share the link of this video via social media platforms like Facebook and WhatsApp so that you can all benefit as a family.